the title already suggests, I'll be talking about what happens when you take small amounts of cellulose nanofibrils and add them into water. Now, the general motivation behind it, though, is much, much bigger and connected to the well-known problem that we're all facing together nowadays, that we need to end our reliance on fossil-based materials and replace them with new sustainable ones in a transition towards a sustainable future. But to actually to be able to do so, we first need to understand these new sustainable materials on the fundamental level to be able to process and develop them properly. With cellulose being one of the most abundant biopolymers on Earth, not the most abundant one anymore, as I found out, and cellulose-based materials being in our everyday life, if it's paper, packaging, clothes we wear, or any wooden utensils we use, one might think that actually we understand the system cellulose water already quite well. But it's actually that we're still uncovering in this field how cellulose interacts with water. So this is an indirect study also of the cellulose-water interactions and their effect on the water dynamics. Now, before we get deeper, let me briefly introduce what kind of cellulose materials I've been working with. There's a cellulose nanofiber, or short CNF dispersants, as I will refer to them throughout the presentation. Now, to get cellulose nanofibers, you start with wood that is first pulped and then mechanically as well as chemically treated to separate the other wood components, such as hemicellulose and lignin, from it. Chemical modification and via the catalyst tempo, shown here on the left-hand side, helps in stabilizing the cellulose nanofiber dispersions by selectively converting the primary alkyl groups on the C6 atom to carboxyl groups. This leads to electrostatic repulsion between them, so we get stable nanofibers and in turn stable dispersions. After the homogenization and purification, you end up with such a stable cellulose nanofiber gel, as shown here, containing mainly water and cellulose nanofibers. It's exactly in these low concentration nanofibrillar systems that are quite underexplored when it comes to the study of water dynamics within them. Now, by adapting the chemical modification, the tempo oxidation, as I mentioned beforehand, and refining this step, you can tune the surface charge and therefore the colloidal properties of these dispersions. In our case, we modified this step so that we get 3 different surface charges ranging from 1.24 to 0.37 millimolar per gram in our case. And why I'm bringing it up is because throughout the presentation, I'll be referring to these as low, medium, and high charged, also represented by these exact colors. Now, having a closer look at these fibers, we can see that they have these chemically modified fibers. They have on average a diameter of 2 to 3 nanometers and lengths of up to 1 micrometer with mean lengths around 300. According to AFM measurements that I conducted. Now that sounds rather small, but from the perspective of a water molecule that I tried to depict down here with a blue, very small bubble, they're actually very big. So also throughout the presentation, gray fibers will represent nanofibers and water molecules I'll artistically represent by water bubbles. Not accurate, but as a descriptor here. Now, to give you a feeling of how such dilute nanofibers actually look and behave in real life, I've brought some samples with me to hand around. Feel free to shake them and observe what happens. Yes, sorry, should start with the opponent first. I do apologize, I went for the first row. Good. Feel free to shake and observe them. So obviously you won't see by the naked eye a change in the water dynamics when you shake them. But as I tried to show in the sketch here, if you've done it properly, then you will see that the air that is introduced by shaking actually will get suspended in here by already in cellulose nanofiber dispersions with concentrations as low as 0.2 weight percent. If you then increase the concentration to 1 weight percent, just 5 times higher, and we're talking here still about milligrams of nanofibers in this water vial, so very, very little amount, you already start to form a gel where the bubbles, air bubbles that you introduce almost seem to get stuck. And that already gives us a hint macroscopically of what is happening in these systems because they strongly interact with each other and can form networks. To now artistically show how I imagine what happens in there, made a little video of what is going on in these dispersions. Good. So now that we've gotten a bit of a glimpse into what might be going on in these dilute nanofiber dispersions, let's have a brief look at the other part of my work, the physical characterization. So what I used to study and quantify the water diffusion with in these cellulose nanofiber dispersions. One of the most commonly used techniques to study diffusion or measure diffusion is nuclear magnetic resonance spectroscopy, or short NMR. The power behind NMR, in short, lies in the fact that the spin of a hydrogen nucleus, like any water molecule possesses, H2O, depicted here now by an arrow, very schematically, can be manipulated as it gives a rise to a magnetic moment that we can then, in the NMR, align and do a few other tricks with. I used a specific pulse sequence or NMR technique called pulse gradient spin echo, where I used magnetic field gradients to manipulate the spin of the hydrogens and therefore measure the self-diffusion in water. So now that we know why I worked with cellulose nanofibers in the first place and what I used to study and quantify the water diffusion with, let's see how I put all of that together in my work. Well, as a first project, I tried to find out how concentration and temperature influence the mobility of water in these dilute cellulose nanofiber dispersions. For this first project, I used a series of dispersions from 0.2 to 1 weight%, exactly like the ones that are going around right now, to give you a feeling. And with different charge densities here, and measured the self-diffusion of water in these systems with NMR at different temperatures from 15 to 35 degrees. Now, as I had 15 different dispersions, I've only picked now for the temperature dependence to highlight it only the extreme cases. So the most concentrated and the most differently charged systems, to show that actually across different temperatures, the trend looks similar. So water seems to be hindered across this temperature range that we chose in a similar fashion in all different systems. That also showed one other thing that we expected. And the left side in this Arrhenius type plot here, maybe I should use PowerPoint. In this left side of the graph, here showing higher temperatures, you see that water diffusion is affected the most. And that also was expected, as diffusion is a thermally activated process. Now, the concentration dependence was much more interesting or puzzling for us, as we got these quite linear trends with the relative diffusion coefficient on the y-axis decreasing with increasing cellulose concentration. Now, that showed that, for record here, to make everyone familiar, 1 up here in the corner is the self-diffusion of pure water, and any number below 1 means water slows down. That way we could see that by adding 1 weight% of cellulose, so the ones that are going around right now, we had a decrease in water diffusivity by almost 4%. Now, comparing that to theoretical calculations, water diffusion should only decrease around 0.5%, as shown here by this line. And if the excluded volume would be the main responsible driving factor for slowing down the water in these dispersions. The excluded volume here, as a definition, is just the volume occupied by the fibers themselves. So it was rather interesting that we saw the strong decrease, and we were wondering what kind of factors could be responsible for this strong change. Well, so exactly, we saw that cellulose nanofibers affect the water dynamics beyond the excluded volume, and we came up with a hypothesis and a few factors that we think influences the water mobility. Well, let's start with the easiest or simplest one first. The more cellulose nanofibers you add in, the shorter your mean particle distance gets in between, simply because you add more. In this case here, we, by a factor of 1.7 down to almost 50 nanometers. And to put that into perspective, that is around 150, 160 water molecules stacked next to each other. So it makes sense that when this gets so confined, so to say, or that in this case also more collisions between the water molecules and the cellulose nanofibers take place. The second factor we hypothesized that leads to this decrease is that obviously the more cellulose we add, the bigger also the surface area gets that's available to interact with the water inside these dispersions. In our case here, by a factor of 5, hindering the water mobility further. Now, the excluded volume naturally plays a role as well, as there's simply less water present when you add cellulose nanofibers in. So that still didn't explain, though, quite why we saw this big drop as we saw beforehand. And as the cellulose nanofibers are somewhat flexible, so they're not stiff rods, we hypothesized that the Brownian motion of the nanofibers, so their movement, their translation, their rotation, and the wiggling of these nanofibers leads in the end to what we call an extended excluded volume due to the dynamic contribution, hindering the water diffusion further. Now, combined, these factors we hypothesized decrease the water mobility, as we saw, and to complement the NMR results, we conducted coarse-grained molecular dynamic simulations on this to verify not only a hypothesis, but also go a bit more mechanistically in depth of how the semi-flexibility in general affects not only the nanofiber dynamics, but also water dynamics. So after this first study brought up more questions and answers, actually, we set out to find what role surface charge, geometry, or gelation play in hindering the water diffusion or affecting it in CNF dispersions, with the general question being, what is the strongest factor influencing water mobility here? Now, for the second project, we compared differently charged CNF dispersions, this time at one concentration only, 0.6 weight%, and looked at them in the ungel state as beforehand and in the gel state by adding sodium chloride. We then also compared them with carboxyl functionalized nanospheres at a concentration of 3.2 weight% and a similar charge here of 0.5 millimolar. Then we measured the diffusion of water with NMR again, and we used quasielastic neutron scattering to measure the mobility of the nanofibers. So to study the effect of surface charge on water diffusion, we compared the cellulose nanofibers here with the carboxyl functionalized nanospheres matched to the same total surface area. That's also why the big difference in weight percentage I mentioned specifically before, from 0.6 to 3.2. Now, as you can see already here, the carboxyl functionalized nanospheres seem to hinder water mobility to a similar extent than the low and medium charged ones. This is here depicted in minus delta D, and to explain that briefly, we before talked about the relative diffusion coefficient. This here is now the difference in diffusion relative to the pure water, meaning higher values in this graph show slower water diffusion, meaning it decreases by around 1.5 to 2%. So it's inverted basically here. Yeah, so exactly. This suggests that the surface chemistry itself plays an important role actually in slowing down the water, with charged surface groups forming hydration layers, which increase the effective volume. That literature research not only showed, but also we conducted atomistic simulations for this that supported this by showing that the surface charge affects interfacial water structuring, as seen here, with surface charge playing a role for all differently charged CNFs, exactly. Now, taking the same kind of set of samples, but now highlighting the effect of geometry, we took the same delta D, but this time looked at it as a function or divided by the volume percent we added. And as we had to add a lot more nanospheres to get the same surface area than the nanofibers, you see now the clear effect of cellulose in hindering water. And that can be explained by looking at the anisotropic shape. Before, as I showed, cellulose nanofibers have a high aspect ratio, so small diameters, very long lengths, and therefore have the ability to form networks already at very low concentrations compared to, let's say, spherical nanospheres here in this case. And that showed that the geometry, in addition with the semi-flexibility, as we hypothesized in the first study, slow down and are really crucial in slowing down water diffusion in these systems. Because water now needs to take more winding and confined pathways compared to a straight A to B random walk. Not fully straight by definition, but to kind of imagine it. Now, with gelation, the whole picture gets a little more complicated as a few things change in our system. First, the addition of a salt leads to surface charge screening, here shown with sodium in yellow, that locally changes the water structure around the fibers. On a bigger scale, that also has implications for the whole system, because now the fibers have less electrostatic repulsion between them. They can get closer together and form a more dense network. As we'll see later as well, that also comes with a reduction in nanofiber mobility. These effects are visible when comparing water diffusion, shown here in absolute values. So to confuse you extra, I had to come up with a third axis. Now we have the absolute diffusion values, meaning higher values, quicker diffusion, lower values, slow diffusion. And with gelation, we can see here nicely that across all three different charges, the right column each time here, corresponding to the gel state, we have a decrease in water diffusivity independent of the surface charge density. So no matter how much charge the fibers had, we still have slow water diffusion in each of these different systems. That also shows us that now the water, so gelation, as we can see now, shows that we add another level of restriction to our water diffusion. So it's not only just the surface anymore and the fiber motion that hinders the water mobility, but now the overall network structure, which becomes more fixed and more dense, starts to play a role in hindering the water diffusion. Using quasi-elastic neutron scattering now, we also measured the nanofiber mobility, so how the cellulose nanofibers move within these systems. And expressed here as yet another diffusion coefficient, I do apologize, DCNF, which translates here to a short translational mobility of the nanofibers, not the center of mass, I want to say right away, but more the local segmental motion of the fibers. And we see two different effects. First, I would like to focus on the difference between the blue data points and the green data points. That also goes back still to our color coding from the start, which shows that highly charged cellulose nanofibers diffuse quicker than medium charged ones. If we think about that the surface charge of the highly charged cellulose nanofibers is higher, they repel each other more, so they give each other more space to move more freely, and there's less friction within these systems when they move, as I interpreted this behavior. The second trend that I would like to focus on is if we look at the light and dark shades that again as before and represent ungelled and gelled systems, we see that as in the high charge systems as well as in the medium charge systems, the nanofiber mobility slows down in both. Now that's actually interesting because we beforehand talk about the dynamic contribution, slowing down water and being so important in hindering the water beyond the static volume. But now we see that they actually in the gel state slow down. So we have a slowdown in water, but also slowdown of fibers. And that explains, or as we now interpret, shows the shift of the nanofiber motion playing a big role in normal dispersions, whereas in gel dispersions, other factors are much more important in restricting water diffusion. So it's the network confinement that plays here a much stronger role than just nanofiber mobility. Now, after seeing that gelation with monovalent ions such as sodium affects not only the water diffusion, but also the nanofiber mobility, we wanted to go one step further and ask what happens if we now change the salt concentration and the type of ion used. For this third project, we used the same set of differently charged CNF dispersions, so that never changes across everything here, but this time we added 3 different salts in different concentrations, sodium chloride, calcium chloride, and aluminum chloride to gel these systems. At one concentration, 0.4 weight%. Then we used NMR as the backbone of this whole thesis to measure the water diffusion and small angle neutron scattering, small or short SUNs to probe the gel network structure. Now, depending on the type of cation introduced now in these systems, the interactions with the cellulose nanofibers are a little different. So let me briefly list what kind of effects we see in these systems. With sodium ions, the main effect is electrostatic screening. So as shown here on the left, that means the repulsion between the fibers is reduced, they come closer together and form a denser network, as we saw in project 2. So that's nothing new, so to say. With calcium ions, though, we still have now the electrostatic screening between the fibers, shown here in the middle by the purple or pink ions, but now we also introduce ion-specific effects. Calcium can coordinate with carboxyl groups and therefore can act as a bridge between different fibers to actually lead to higher connected structures. With the addition of aluminum ions, the interactions become even stronger. So because of its higher charge density, aluminum can coordinate way more strongly now with several carboxyl groups compared to before and to sodium and calcium, and leads to very dense and highly interconnected structures. For the record as well, these are schematics I want to throw out, so don't look at them too closely. Depending on the cation now, different ion-specific mechanisms govern the structure of the network and dynamics. And to show you now what I measured with 3 different salt concentrations, 3 different salts and 3 differently charged systems, you end up with a lot of data. So everyone who had to go through the thesis, especially committee and opponent, I apologize. It's been a lot of graphs. I cut it down here for the presentation and just picked out a subset of highly charged cellulose nanofibers to show what is going on. So here on the left, we have the relative diffusion coefficient as always. Quick reminder again, 1 being the diffusion of pure water and anything below being slower. On the right side, we have Xi in nanometers. That's a parameter that I use to, that comes from small angle neutron scattering and is a fitting parameter. And how I interpreted it is the effective length between, or an effective measure with, to measure the distance between entanglements in this gel structure. Now, let's focus on what we can see here. Let's start easy, or let's start with the easiest one and look at sodium chloride, depicted here in yellow. Now, with sodium chloride, the water diffusion as well as the correlation length change only minimally, as you can see here, with very slow decrease across, and just highlighting the effect of electrostatic screening on the water dynamics and gel structure. With calcium chloride now, following the red lines underneath directly, we see that a much stronger effect in decreasing the water diffusion and the correlation length. And we can see that the bridging between the fibers leads to a tighter network, as seen here in lower correlation lengths, and therefore also slower water diffusivity in these systems. With aluminium-free plus ions now, shown by the blue lines, and also showing the strongest decreases here in correlation length and diffusion, we get really a strong suggestion that the complexation, so how these aluminium ions interact and coordinate with the carboxyl groups and the overall network confinement, start to play a huge role in hindering water diffusion. If we remember now project 1, we saw that adding 1 weight% of cellulose led to roughly 4% decrease in water diffusivity. Well, now we have here with aluminium chloride a decrease by almost 20%. So we have a huge, huge effect. And this just in the CNF dispersions with 0.4 weight%, so way, way lower than beforehand. Just highlighting how much gelation affects the dynamics within the system. Good, and then the last project now, project 4, we set out to combine some of the elements of the other projects and see how added nanoparticles influence the structure, network structure of the hybrid systems and also the water dynamics within these. There we focused on the charge, nanoparticle charge, and also the nanoparticle sign or charge sign of the particles. Now, what am I talking about here is we used again our anionic CNF dispersions at one concentration, 0.4 weight%, and then combined them with differently, with anionic and cationic latex nanospheres at a ratio of 3:1, because we wanted to see their additive effect to the network structure. We then used NMR again to study the water diffusion in these hybrid systems and used contrast variation SUNS, that's a special small angle neutron scattering technique, to match out certain components and probe the different lengths within this system. Now, in the, here we can see in this, we start easy again with the low charge system. In this graph, we see on the left side, the relative diffusion coefficient, as I've been talking about the whole time, in blue, depicted by the blue lines. And on the right side, the same correlation length I described beforehand, shown here in orange. Now, what we can see right away is that depending on if the nanoparticles that we added now have the same charge sign, so if we add likewise charged particles or oppositely charged particles, plays a huge role in the structure and diffusion dynamics in the system. And to put that in numbers, I here on the x-axis have the surface charge ratio, which I defined as the ratio of the nanoparticle charge to the cellulose nanofiber charge. So it's a global charge balance, so to say, the expression. Now, let's focus in on the left side. We have anionic nanoparticles added. In the middle, we have the reference system, and here we have the cationic, so opposite charge. Well, in systems with a similar charge, they repel each other, and not much happens. We have barely any change in correlation length, so in characteristic lengths in the system barely change. And also the water diffusion in these systems doesn't seem to be affected much. Now the opposite trend or the picture completely changes when we add oppositely charged nanoparticles, because now they start to interact with each other. This behavior we interpreted as the absorption of the cationic nanospheres onto the fibers. So they start to act as connection points between the fibers. And the network densification then leads to water diffusion. That makes logically sense, but the interesting part is if we now look at the highly charged systems. The highly charged systems, it looks completely different. And the addition of anionic nanoparticles, well, this is, again, as before, and barely changes diffusion or the structure, but now it doesn't decrease the water diffusion anymore. I know the error bars are huge, and this is something that we're still working on. That's why this is a manuscript in preparation. But I trust my data. That sounds very wrong, but what I can say with certainty is at least it doesn't decrease the water diffusion anymore. So how can we picture that? And why does that happen? For that, we have to look at the surface charge ratio beforehand again. And beforehand, we had values of 1 and 2, etc. So higher ones, which makes sense because we looked at low charged fibers and nanoparticles with a stronger, relatively stronger surface charge. Now, in this case, we look at highly charged fibers, meaning we have way stronger interactions between the components. So how we interpreted this now is that the nanofibers here start to really interact with the nanospheres. So they drape and attach, and the nanospheres become points of aggregation. That means we get a more heterogeneous network, which means still that it densifies in certain areas, which the correlation length can show, but the water diffusion doesn't change anymore. Because now we also have areas in between with less confined water that can allow water to diffuse through. So the takeaway of this one is that the strong local interactions actually govern diffusion in these hybrid systems. Now, to summarize now, I've looked at water diffusion in different CNF dispersions, hybrid systems, and other nanoparticle systems as well with spherical geometry, with several factors influencing the water diffusion in these systems. Increasing volume and surface charge reduces water mobility, while the surface charge itself affects the hydration layering around it, and therefore the effective volume that the water is affected by. The nanoparticle geometry and semi-flexibility amplify this effect with the dynamic contribution as we hypothesized, and leads to further slowdown of water. In gel systems, salt screening restricts not only the fiber motion, but also leads to a more confined network. And finally, in hybrid systems, it's not just the global charge balance, but actually the nanoparticle charge itself that that controls whether these particles either coexist merely or actually lead to a restructuring of the network as we now interpret it with these differently charged CNF dispersions through the electrostatic interactions. Now, with this, I would like to conclude my talk and come to the acknowledgements, because let's face it, I could have not done this without many, many people. So special thanks go to my supervisor and co-supervisor, Daniel Söderberg and Anastasia Ryazanova, who guided me through here, and also the lovely group of fiber processors that I'm thankfully part of. I also want to thank many other people that helped out in this research, where I had to nag for chemistry questions, learn about NMR, or get very beautiful nanoparticles. I have an address I can send you to. I also would like to thank everyone that helped me at ANSTO. So last year I went to Australia to conduct the neutron scattering experiments. I had a supervisor there as well, Elliot Gilbert, who greatly, greatly helped me and brought this project to a way new level, I would say. And also would like to thank everyone at Malmö University who I had the pleasure of working with over the years, who've been always there. And lastly, obviously my sponsors. So we shouldn't leave without thanking them. No, I met really nice people, and unfortunately there's no better picture on there. I know it's pixelated. I tried last night to find a better one, but thank you to all of them as well for the journey. So thank you also for your attention. Now I've said enough thanks. And that leaves only one last thing. Are there any questions? Thanks.